In last video we calculated the alpha m value which is 1.37 less than 2.5. Now we can also obtain this 1.37 with this equation if the bending moment diagram is known. We can also use table 5.6.1 that is on page number 62, table 5.6.1. In here we can respectively find the bending moment diagram. So that bending moment diagrams is look like in this fashion. So we can check this diagram. Equivalent diagram is here, which is very close to this one, where we have this a value is 0, so this will be in the center. So these values, these diagrams look like in the center. So in that case, a equal to 0, we should find the alpha m value. We are able to find alpha m value which is 1.35 plus 0, because a is 0. A is the distance from the midpoint to the force where is acting along the beam. So the force is acting at the midpoints in our examples, that is force is acting at the midpoint. In that case, a equal to 0, so we have 1.35. so that is just a quick verification that calculations we done using the equations. That's 1.37 is approximately alpha m value 1.35 in table 5.6.1. Now next step, we need to find the slenderness reduction factor alpha s. Now beam is partially restrained at both supports p, so it means that is given here. The beam is partially restrained at the end where the lateral deflection are effectively prevented, and so on. So in the question is given these conditions. For that conditions, we should be able to say that is a partially restrained condition at the both ends. So we can say that p condition here, that is 10 for pp. Now in here we first find the twist restraint factors kt. Now the twist restraint factors kt, we can use the table that is on table 5.6.31 on page number 64. Twist restraint factors, various restraint arrangement is given. Now in our case is given partially restrained both hand, so we should be able to use this equation 1 plus so on. Now that copied here. Now I can explain this one parameter, each parameter one by one. So 1 plus that I think that's 2 is not needed. It's just extra 2 there. 2 d1. What is d1? On page number 14 one still tables, we can find that d1 value, which is the depth of the, that is here 460 ub 67.1, and the d1 value is depth between the flanges, which is 428 millimeters, that is given here, and that's d1 is the one that is between the flanges. So 428 millimeters, that is 428 millimeter. Length is given in the questions. As you can see, the length of the two supports are given 8000 millimeters. So 8000 millimeters times the thickness of the flange 12.7 millimeters. Back to the one still tables, and thickness of the flange tf 460 ub 67.1. Thickness of the flange is 12.7 millimeters. That is the value for thickness of the flange. Thickness of the web, which is 8.5. We have from one still tables, thickness of the web is 8.5 millimeters. That is 410 ub 67.1, and thickness of the flange 8.5 millimeters. Now once you substitute to the power 3, and number of webs is only one web. For example, this one here, how many webs we have in the one still? So we have only one webs, 406 ub. There is no any details about number of webs, so there is only one web, so that is 1. So simply calculations give kt equal to 1.05. Now load height factors KL, few details are needed to extract the KL value, which is the load height factor KL. We first need to know longitudinal position of the load. I think is within the segment or segment end. So that red color one, which is restrained at the supports only, then it is within segments. It's given in the questions. In the questions it says that restraints available only at the supports end. So for example, restraint is here, so that means that is within the segments. If we have a restraints given in the middle where the load position as well, so we may classify that one is at the segments end. So in our examples we have within segments, so therefore first condition, load is within segments as shown here. Now restraint arrangement, we need to second column is the restraint arrangement. We have find the PP restraint arrangement, so we have this PP value here, so it's the first row. And then load height position, top flange, we have load height position either in the shear centers or top flange. I think in the question it says that all the loads are applied to the top flange, so therefore this classification is here top flange. In this case within segment PP top flange we have a KL value which is load height factor 1.4, so that is 1.4 from table 5.6.2 on page number 64. Now lateral rotation restraint factor KR, as we know that is from here, lateral rotation restraint table 5.633, we have a restraint arrangement is a PP, so we have restraint arrangement there are PP, that's 3 rows, but we need to find N with the lateral rotation restraints. We have N with lateral rotation restraint nuns, as you can see there is in the questions. It says that twist rotation are partially surface, so it's not restraint, so that's rotation, lateral rotation is not restraint, so it's a none, so we have a value none. And for PP we have KR value is 1, so we take KR value equal to 1, that is on the next page, KR equal to 1. Now effective length LE, we have an equations on the page number 63. Effective length LE is equal to KT, KL, KR and L. Now we found all the factors. KT we just found, which is twist rotation factors in the previous step 1.05. We find KL load height factors which is 1.4, that is here, and KR lateral rotation restraints KR we found just here 1. Substituting all this value, length L is 8,000 millimeters, that is given in the questions. Like in the questions the distance between two support is 8,000 millimeters, so that's multiplication gives 11,760 millimeters. Now there is a big equations, reference buckling moments, M0 is equal to pi square E Iy Le square Gg plus pi square E Iw Le square. That equation is taken from Australian standards. Now on page number 59 we have somewhere here in the equation 5.611 in the middle of the page we have these big equations that is taken from here. Now this is a big equation, so I'm just break it down into 3 different sections. Here pi square, first I'm going to calculate this pi square E Iy Le value. Pi square E is the Young modulus of the steels. If you go to the Australian standard on AS4100 on page number 14, the Young modulus of the steel is given 200,000, so that is 200,000 E. Iy is given in the Australian in the one steel table, 467.1, and Iy value is 14.5, so we can find 14.5 Iy, and please note there is 10 to the power 6 multiplication, so that is, so Iy value is 460 UB 67.1, and that Iy value is 14.5, 10 to the power 6. That is 206 divided by Le, we just found 11,760 millimeters square, and then we have these big numbers here. We need to be careful here in the calculations. Now G is the shear modulus, that is again taken from Australian standards. On page number 15 AS4100 we have a G value, shear modulus of elasticity 80,000, that is the G value. Now that's G value. J is taken from one steel table, 460 UB 67.1, and there is a J value which is 378 and times to the power 3. Please note there is a 10 to the power 3 here for this 378 J value. So that is 378 times 10 to the power 3, and multiplication gives this one. Similarly, we can have pi square. E value is from Australian standard. Iw is the wrapping factor coming from one steel tables. 460 UB 67.1. Iw is 708 10 to the power 9. So 710 to power 9 divided by 11760, and that's the value for these three. So now I'm substituting those three different values. So one by one, this one is 206,958, GJ is this value, and this value is this one. Give us these big numbers here: 91.3 10 to the power 6 and 91.3 kilonewton meters. Please check these numbers, okay? They should not be in the millions and more, like not 10 to the power 6, something in the thousands, 2000s range, or 500 or 100 range kilonewton meters. So always, because there is a big numbers here, it is easy to make some mistakes to not do the square root or some multiplication or addition. So please check these numbers. That should not be too high or too low. Now slenderness reduction factor alpha s. Alpha s is given in the page number 59. On page number 59, alpha s 0.6 ms over MOA square plus 3. Please note this 3 is within the square root, and we need to multiply 0.6 with the whole bracket. Now 0.6 section capacity we found in the previous steps. We found this section capacity 444 kilonewton meters, so that is 444 kilonewton meters. We find MO value 91.3 plus 3. Please note this 3 is within the square root, okay? So let me put this in the bracket. Minus section capacity over MOA 91.3 give us 0.18. Now alpha m times alpha s. Alpha m we just found in the previous steps. Alpha m we find 1.37, so that is 1.37 times 0.18, and that factors give us less than 1, should be okay. If it is should not be greater than 1, otherwise we need to take it as a 1. Now member moment capacity MB is alpha m alpha s ms 0.247 that we just calculated, times the section capacity is 444. That section capacity we calculated in the previous steps, which is 444 kilonewtons. Multiplication gives 109 kilonewton meters, which is less than 106.4. Now member moment capacity, once we find 109 kilonewton meters, we can find 5 MB. In fact, safety factor is 0.9 times 109 kilonewton meters, that is given 98.1. Now we should compare this member capacity that we calculated with the bending moment diagram. So bending moment diagram will give the design bending moment. So 106.4, we should get this value more than 106.4, then only the condition is satisfied. So in here Australian standard is saying in the page number 49 on clause 5.1, saying that mx star, which is coming from the bending moment. So this is coming from bending moment, design bending moment about x-axis. So we that is 106.4, that is given here, that is 106.4. Should be less than 5 mbx, that is we calculated, that is clause 5.1 on page number 49. But in our case 106.4, that is coming from this bending moment diagram, is not less than 98.1. so that is not okay, right? That is our beam is not enough to carry that 106.4. so this 106 UB 67.1 that is given in the questions, 460 UB 67.1 that is given in the question, is not enough to carry this 106.4. so we need to just go one above the higher value. So where we gonna find that higher value? If you check the one still tables, if you go more above, like 460 UB 67.1, if you go more than this one 460 UB, then it should have a higher capacity than 98.1, and we may be able to go more than 106.1. repeat all the procedures again if you like to check whether this is enough or not, but this is just quick exercise to show that the given universal beam is not okay when you compare with the bending moment diagram. Thank you.